number theory, and yeah, so we will start with a warm-up problem, which should be on the screen now. It's find all integers a and b such that a times b is equal to 100. Okay, so hopefully that was enough time. Now I'll go over how to do it. So, ooh, here's the problem. A bit got cut out. Ah, okay. Find all integers a, b such that a times b is equal to 100. So, we try, for example, say a equals to 2, and b is equal to 100 over 2, which is equal to 50. And that works. If we keep trying, for example, a equals to 4, b equals 100 over 4, which is equal to 5. However, if, for example, a is equal to 3, then b is equal to 100 over 3. It's equal to not an integer. So what we notice is a has to be has to be a factor of 100, so that when b is equal to 100 over a, it's an integer. So the factors of 100 are 1, 2, 3, 4, 5, 10, 20, 25, 50, 100. Yeah. So if a equals if a is equal to 1, then b is equal to 100. If a is equal to 2, b is equal to 50, 4, 25, 5, 20, 10, 10, 25, 25, 4, 52, and 101. But we're not done, right? Because the answer asks for integers, but we've only given half of the answers, right? Because, for example, if A is equal to -1, B is equal to -100. So all the answers are -1, -100, -2, -50, -4, -25, and so on. So that's what the solution is. Now we will move on to the next problem. Does everyone understand this? Sorry. Okay, hopefully the problem is now up. Okay, so now I will present the solution. In the previous problem, we were looking for all integers. We were asked to find all integers a and b such that ab equals to 100. And this was very easy by just going through all the factors of 100 and checking what happens if a is equal to one of those numbers. But this 5ab equals 25a plus 4b is a bit different. So first, let's just move everything to the same side. And now, after doing the previous problem, we would like it if we could find two variables or two things that multiply to some number. For example, this. And then we can go through all the factors. So this one's AB, and this one's just A, and this one's B. So that inspires something like this. But this is 5AB, so let's just put 5 here, let's see. And then we need the 25A, so minus 25. And this is a bit problematic, correct? Because this is no longer an integer. And when we solved this, we relied on the fact that A and B are both integers. So let's try again. Let's say instead of placing the 5 here, we'll put the 5 there. Then to make the 4b, we do that, and to make minus 25a, we do that. And then there's also a negative 4 times negative 5, which equals 20. So now we can check the factors of 20, which are these, and we can go through all of them, right? If b minus 5 equals 1, then 5a minus 4 is equal to 20. If b minus 5 equals 2, then 5a minus 4 equals 10, b minus 5 equals 4, 5a x4 is equal to 5, and so on. And then, of course, we also have to check the negatives as well. And, but if these are not all solutions, right? Because, for example, this would mean c is equal to 6, and a is equal to 24 over 5, which is not an integer. So, no solution. What about when b minus 5 is equal to 2? And b is equal to 7, and a is equal to 14 over 5. Again, no solution. In this case, b is equal to 9, and a is equal to 9 over 5. No solution. Let's see if there even exists a single solution to this problem. b minus 5 is equal to 5, then 5a minus 4 is equal to 4, which means a is equal to 8 over 5. No solution. No solution. Well, here is a solution. It means b is equal to 25 and a is equal to 1. So a, b is equal to 125. And if we substitute that back into the equation of 5a equals 25 plus 4b, left-hand side is equal to 5 times 1 times 25, and right-hand side is equal to 25 times 1 plus 4 times 25, so 125. And that's the solution. So we just gotta finish checking all of them. We're done with all of the positive ones, right? 20, 10, 5, 4, 2, 1. And yes, there was some negative ones, right? We got negative 1, negative 2, negative 4, negative 5, negative 10, negative 20. This factorization is a very common technique, actually. In easier problems, the entire problem, such as this one, may be solved by this one technique. However, even in more advanced problems, a lot more advanced problems, this can still appear as a minor part of the whole problem. So basically, for any constant, let's say, okay, let's say we have a problem of the type so that axy plus bx plus cy plus d equals 0. A, B, C, D. constant integers. And how would we factorize this? So again, we want something like this, right? Something x plus something times something y plus something equals to something. But in front of the x value is an a, and this is quite problematic because, right, like, what do we do about this? Do we like a1? But then how can we be sure that we can get cy? There's an a here. So to deal with that, we multiply this whole thing by 8. Now we got a squared xy plus abx plus acy plus ad is equal to 0. This is very easy to factorize, right? Plus b plus c is equal to bc minus ad. These two are the exact same, right? You can check this if you want to. And so now we just have to, now we just have to go through the factors of bc minus ad and go through all of them, right? And this technique is called Simon's favorite factory trick. I think that's what it's called. Simon's quite cool. He may have invented this factoring trick. Very smart fella. Okay, next problem. Oh, okay, but by the way, the previous topic was factorization because, yeah, we factored 100, and in this case, we factored this expression and then went through the factors of 20, which was the constant remaining at the end after using Simon's favorite factor. And factorization is a very common technique involving integers because the definition of factors and divisibility is very reliant on integers. Next technique is bounding. So this is where you solve a problem using upper or lower bounds. And also, in the previous two problems, there was a lot of bashing, right? We had to go through all of the factors. It's a common theme in these problems because, again, after you bound, let's say x is between 5 and 10, then we know x has to be 6, 7, 8, or 9 because we know x is an integer. So this technique can only be used with integers, right? Because say we know x is between 5 or 10, and x is a real number, that doesn't give us very much. Okay, so try this problem for a bit. So hopefully you all had an attempt at the problem. Okay, so when you see this problem, the first thing you should, okay, well, there's two things you might think about that are both correct. Firstly, you might try to expand the left-hand side, or you might also realize that y, the variable y, is quite useless. You can kind of just reword this problem as find all integers x such that x plus 2 to the power 4 minus x to the power 4 is a cube. Right, there's nothing really special about y. Okay, but the other thing we might notice is we can try expanding the left-hand side too. And then that would give us 8x cubed plus 24x squared plus um what, yeah, 24x plus 16. Mm, hold on. No, no, no. 16. No, no, 64. Yeah. Wait, no, 32. Okay, sorry. Yeah. Okay. Is equal to y cubed. And let me make sure this is correct. Yep. Okay, so that's the cube. This is the cube. And if we look at the big term, that's roughly 2x cubed. Especially as x becomes super duper big or super duper tiny, this number is basically 2x cubed, which means y is roughly 2x. But this should be bigger than 2x cubed because this also contributes to something. So let's try what 2x plus 1 cubed is equal to. 2x plus 1 cubed is 8x cubed plus 12x squared plus, nope. Oh, no, yes, 12x squared plus 6x plus 1. Um, how does this compare to that? 8x cubed plus 24x squared plus 32x plus 16 minus 8x cubed plus 12x squared plus 6x plus 1 is equal to 12x squared plus 26x plus 15, which is equal to let's see, equal to x plus 2 squared plus 12x plus 1 squared. Yeah, no, 411. Yeah. Okay, why did I think of putting it into squares? Okay, so my feeling was, since this is 24x squared and this is 12x squared, this should be bigger than this, I think. So if we subtract it, we want a positive number. So if we can get some squares, this is always positive, because squares are non-negative, and we can't have both of them being zero. So this is just always positive, and this is always positive. So y is always bigger than 2x plus 1. What about 2x plus 2 cubed? That is equal to 8x cubed plus 24x squared plus 24x plus 8. This looks very close to that. Oh no, oh, okay, that's quite sad. Um, yeah, I can't get back to it. But for example, if x is equal to -1, then y would equal to 2x plus 2. So we have a feeling that y is roughly equal to 2x plus 2. Um, so what about 2x plus 3 cubed? That's equal to 8x cubed plus 36x squared plus 54x plus 7. And I feel like this is always bigger than y cubed. So let's subtract it. And equal to 12x squared plus 22x plus 11, which is equal to x squared plus 11 times x plus 1 squared, which is always bigger than 0. So therefore, 2x plus 1 cubed is always less than y cubed, which is always less than 2x plus 3 cubed. But we know y cubed is a cubed number. So therefore, y is equal to 2x plus 2 cubed, because that's the only cube in between these two, which means 8x cubed plus 24x squared plus 24x plus 8 is equal to 8x cubed plus 24x squared plus 32x plus 16. This is the expression for y cubed. This is 2x plus 2 cubed. That becomes x equals -1. And it also means y is equal to 0. And that is indeed a solution. Because if we sub it back into the original problem, x plus 2 to the 4 minus x to the 4 equals y cubed, then RHS is equal to 0 and RHS is 0. And this is the only solution. So the key insight was to notice that y, variable y, looks very close to 2x. And if we look at the possibilities of the numbers around 2x, we looked at 2x, 2x plus 1, 2x plus 2, 2x plus 3, we notice that y can only be equal to 2x plus 2. And then after we notice that, then it's just a basic find x, which is very easy. Okay, next problem. Find all ways of writing the number 1 as a sum of the reciprocals of 3 positive integers. By the way, when I say the technique is bounding, that's a very vast number of techniques. For example, in the last problem, we bounded what a certain cube number could equal. And this one, we have a very different type of bounding. Okay, so first I'll give a quick hint. Um, okay, so this problem is very wordy, firstly. So let's fix that. Okay. Let's say A, B, C are positive integers such that 1 equals 1 over A equals 1 over B equals 1 over C. Now it's more mathematical. That's quite nice. Okay, so now I will cover a very common little step in a lot of problems. Right. We notice that the variables A, B, and C, they perform completely the same function, right? So let's say I'll give out a solution. A, B, C is equal to 2, 3, 6. 1 is equal to 1 over 2 plus 1 over 3 plus 1 over 6. But what if we scramble the order of it? Let's say A, B, C is equal to 6, 2, 3. This is still a solution, right? So we can mix around the order however we like. And since we can do that, we can give ourselves some conditions, some extra conditions that we can derive. Mainly, we can order them. Yeah. So we can just scramble them such that that is true. And we're not losing any generality, right? We're still looking at all possible solutions. Let's say eventually we find that 244 is a solution. Then that also means 424 is a solution, and 442 is a solution. We're just going to reorder them at the end. So, uh, abbreviation that's always accompanied is WLOG, which is about loss of generality. This basically just means we are not losing any generality. We are still looking at all possible solutions, but at the end we just gotta remember to scramble them up and all possible reorder. By the way, you can play around with this for a bit. But now I'll continue with the rest of the solution. So you also know this, right? One within. So then that means 1 equals 1 over A plus 1 over B plus 1 over C. But that is greater than or equal to 3 over C. And it's also less than or equal to 3 over 8. So let's see what these ones give us. First one is greater than or equal to 3 over C. That gives that C is greater than or equal to 3. That's quite useless because C can be equal to 4, 5, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. What about this inequality? That gives us that 3 is greater than or equal to 8. That's pretty good, right? Because that means A can only be equal to 3, 2, or 1, because it is a positive integer. If A is equal to 1, then 1 is equal to 1 plus 1 over B plus 1 over C, which doesn't work, because this can't be 0, because they're positive. What if A is equal to 2? Then 1 is equal to 1 over 2 plus 1 over B plus 1 over C, which means 1 over 2 is equal to 1 over B plus 1 over C. Now we're stumped a bit, right? Obviously B has to be greater than 2, because otherwise this is too big. So let's say if B is equal to 3, and 1 over C is equal to 1 over 6, means C is equal to 6. That works. What if C is equal to 4? Then 1 over C is equal to 1 over 4, which implies C is equal to 4. Also, if B is equal to 5, then 1 over C is equal to 3 over 10. Doesn't work. And C equal to 6, 1 over C is equal to 1 over 3, which means C is equal to 3. That works, right? But we're forgetting a condition. C is bigger than or equal to B. Wait, hold on. Yeah, and B is equal to 6 and C is equal to 3, which doesn't work. So we realize once B becomes too big, there are no more solutions. Because 1 over 2 is equal to 1 over B is equal over C, and that is less than or equal to 2 over B, which implies B is less than or equal to 4. So let's check. And now we know all of this, right? That means B is equal to 4 or 3 or 2 or 1, but also B is greater than or equal to 2. I mean, greater than or equal to A, which is 2. So we eliminate those. If B is equal to 2, then this doesn't work. If B is equal to 3, then we got this solution. And if B is equal to 4, then we got this solution. So we got 2 solutions. Now we still have to check if A is equal to 3. And if we use the same technique, then we know that B and C are both greater than or equal to 3. But they both need to be pretty big, right? So B has to actually be equal to 3 and C equals to 3 as well. So that 1 is equal to 1 over 3 plus 1 over 3 plus 1 over 3 by the exact same reasoning. So we got another solution. And now we have to go back to this, right? We have to remember that we reordered them. So all the solutions will now be this one, 2, 3, 6, 2, 6, 3, 3, 2, 6, 362, 693, 632. And this one, 244, 424, 442, and this one, 333. Okay, next problem. Now we move on to the next topic, which is modular arithmetic, which, if you remember, is looking at the remainders of a number when divided by another number. I think since this idea is probably very new to many of you, I will go over it, or part of it already. Um, yep. So show that the equation x to the 4 plus 131 y to the 4 is equal to 3z to the 4 plus 2000 has no integer solution. If we recall, mods basically look at the remainders of numbers. For example, 99 is congruent to 3 mod 11 because 99, nope, 3 mod 32 because 99 divided by 32 is equal to 3 with remainder 3. Oh, that's a bad example. Let's say 8. 99 divided by 8 is equal to 12 R3. So here you can see 98, 8, and 3. And this number is ignored. So this says that 99, when divided by 8, leaves a remainder of 3. Why is this useful at all? When we see powers of numbers, for example, x to the power 4, that often implies you should consider the mods of the equation, the expression. Because let's consider the mod 5 and powers of 4. 1 to the power 4 is congruent to 1. 2 to the power 4 is congruent to 1. 3 to the power 4 is congruent to 1. 4 to the power 4 is congruent to 1. That's quite cool. And 5 to the power 4 is congruent to 0. Power 4 congruent to 1. 7 to the 4 congruent to 1. 3 to the 4 congruent to 1. Oops. 8 to the 4 congruent to 1. 9 to the 4 congruent to 1. 10 to the 4 congruent to 0. Okay, so this is our hypothesis, right? A power of 4 is always congruent to 0 or 1 mod 5. And this line proves it, right? Because say x is equal to 5n plus r, where f cubed, where these are just two variables, then x to the 4 is equal to 5 cubed plus r to the 4, which is equal to 625 cubed to the 4 plus 500 cubed 3r plus 150 q r squared plus 20 qr cubed plus r to the fourth. And we can see this is just congruent to r to the fourth multiplied, because these are all congruent to 0. And r is the remainder, right, which is 0, 1, or 0, 1, 2, 3, or 4. Yep. And that has to be 0 or 1. So that is our Newfound information. Now let's look at this equation. X to the 4 plus 1, 3, 1, y to the 4 is equal to 3, c to the 4. That's 2000. If we look at mod 5, x to the 4 plus 1, 3, 1, y to the 4 is congruent to x to the 4 plus y to the 4. Because 1, 3 is congruent to 0. Mod 5. And 3c to the 4 plus 2000 is congruent to 3c to the 4. So now we have x to the 4 plus y to the 4 congruent to 3c to the 4 mod 5. Um, hmm. Oh, okay. Yeah. So let's see. If x to the 4, still a little table. If c to the 4 congruent to 0, then x to the 4 plus y to the 4 0 mod 5. And we notice the only solution to this would be x to the 4, y to the 4 congruent to 0. Both of them are congruent to 0, mod 5. What if c to the 4 is congruent to 1? Then x to the 4, y to the 4 congruent to 3, z to the 4 is congruent to 3 mod 5. And we have two terms, both of which are 0 or 1. That can't become 3. So no solution. So we have something, right? Z to the 4 congruent to 0, x to the 4 congruent to 0, y to the 4 congruent to 0. So y 5 divides x to the 4, y to the 4, and z to the 4. And that means 5 divides x and y and z, right? Because 5 is a prime. But then that means 5 to the 4 divides x to the 4, y to the 4, z to the 4. And we have x to the 4 plus 131 y to the 4 minus 3z to the 4 equal to 2000. This is divisible by 5 to the 4, but 2000 is equal to, if we prime factorize it, 2 to the 4 times 5 to the 3. So 5 to the 4 is equal to 625 does not divide 2000, but 5 to the 4 divides left-hand side equal to 2000. That's contradiction. So therefore, no solutions. The key idea here was to realize if there's powers of numbers, we should try some mods and see what happens. This doesn't always work out that well because let's look at some other mods. Let's say mod 6. Right, 0 to the 4 congruent. 0, 1 to the 4, 1, 2 to the 4, congruent to 4, 3 to the 4 congruent to 3, 4 to the 4 congruent to 4, 1 to the 4 congruent to 1, 5 to the 4 congruent to 1. So therefore, x to the 4 is column 0, 1, 3, or 4. 1, 6. That's not as cool as this, right? This is so limiting. It's really useful. Okay, next problem. That the equation 5n squared minus 6n plus 7n squared equals 1985 has no solutions. Okay, hopefully that's enough time. This looks like a quadratic, right? We have m squared, m times n, and n squared. So let's rearrange it. And that becomes 5 m squared minus, that's a quadratic. than m squared. Hopefully, you've all learned about quadratic equations at school. If not, a quadratic equation is just something times a variable squared plus something times a variable plus something equals 0. And we know the solution for x is negative b plus minus square root b squared minus 4ac, and all of this over 2a. So that means n is equal to 6n plus or minus square root. Mm, um, oh, negative 6n squared minus 4 times 5 times 7 n squared minus 1985. And all of this divided by 2 times 5. And clearly the problematic term is that if we want m to be an integer, this thing clearly has to be, the thing inside it clearly has to be a square. Otherwise, we get some irrational numbers, and that's just nowhere near being an integer. So negative 6n squared minus 4 times 5 times 7 n squared minus 1985 is a square. And this is equal to 36n squared minus 140n squared plus 3700, which is equal to 3700 minus 104. Let's try some numbers. We want to prove that this is not a square, because we want to prove there's no integer solutions. So let's pick a mod that removes the variable, because this is quite hard to deal with. So I'm going to pick a factor of 104. Let's say we look at the expression in mod 4. 0 squared congruent to 0, mod 4. 1 squared congruent to 1, 2 squared congruent to 0, 3 squared congruent to 1. So x squared congruent to 0, 1, mod 4. But 37000 minus 104n squared, or actually, um, hey, different approach. 37000 minus 104 n squared. That is divisible by 4. And then we get, oh, okay, I see the problem. I made a mistake. Yeah, this should have been 39700. However, let's keep going with factoring out the 4. 37000 minus 104n squared is equal to 4 times 9 and 9, 925 minus 26n squared. So that's is a square if and only if 9925 minus 26n squared. Yep, because 4 is a square, and if we divide a square by a square, it should still be a square. So now let's try some mods. we know that x squared is equal to 0 or 1 mod 4. So let's look at this thing. 9925 minus 26 in squared is congruent to 1 minus 2 in squared, mod 4, which is congruent to 1 or 3. This doesn't really do much, because a square can be congruent to 1 mod 4, and this thing can also be congruent to 1 mod 4. So let's keep trying. Mod 5. Um, 0 squared congruent to 0, 1 squared congruent to 1, 2 squared congruent to 4, 3 squared congruent to 4. This one doesn't seem as useful. Oh, also, if we look at this, yeah, it's just, this doesn't seem very good. What about mod 6? 0 squared congruent to 0, 1 squared congruent to 1, 2 squared congruent to 2, 3 squared congruent to 3, 4 squared congruent to 4, sorry, 5 squared congruent to 1. This can be 1, 2, 3, or 4. X squared congruent to 0, 1, 3, or 4. This, again, doesn't look very useful. What about mod 7? 0 squared congruent to 1, 1 squared congruent to 0 squared congruent to 0, 1 squared congruent to 1, 4, 2, 2, 4, 1. So we have 0, 1, 2, and 4. This also not very promising. Well, mod 8. So we got 0, 1, or 4. That's quite good. So let's try mod 8. Um, I'll delete these. Alright, this was our process of trying to look for a mod that will help us. So now let's look at this mod 8. 9925 minus 26 n squared is congruent to 5 minus 2 n squared, which is congruent to 5 or 3 or 0. Or 5 mod 8, because, right? N squared is 0, 1, or 4. If it's 0, then we get 5. If it's 1, then we get 3. If it's 4, then 5 minus 8 is negative 3, which is congruent to 5. But 3 or 5 is neither of these. So, therefore not a square. And we're done. We've proven that this is not a square, so there are no integer answers for m. Next problem. Find all integers x and y such that x to the 4 plus 2x squared y plus y cubed is equal to 0. Now we will look at a new technique which involves using the greatest common divisor, the GCD, of some numbers. You'll realize a lot of these techniques are very involving divisibility, and that's because, as I stated earlier, divisibility is a very fundamental topic of integers. Okay, so here's what I mean by choosing the GCD. Let's say let D equals GCD X and Y, and oh, and maybe what the GCD is called the HCF, the highest common factor at school. GCD is the more internationally used way of saying it. So yeah, but call it what you like. HCF is definitely also fine. Let's say x is equal, and then let's say let x equal x over b, and y equals y, which means x equals xd and y yd. And you know that GCD x and y is equal to 1. Because if something divided x and y, then it would just go into d and exit x and y, right? So therefore nothing divides x and y. Now what happens to the expression? Then we get d to the 4 x to the 4 plus 2 d cubed x squared y plus d cubed y cubed. Um, Let me try and make this a bit easier to read. And now we can divide out the d cubed, right? Because this is equal to 0. So we get d x to the 4 plus 2x squared times y plus y cubed is equal to 0. And now what? Why did we even use this? Um, now it comes into use, right? Let's say if some number p divides x, then dx4 plus 2x squared times y cubed is equal to 0. Uh, then y cubed is equal to negative dx or minus 2x squared times y. And p divides x, so p divides the right hand side because we can factor out x, which is equal to y cubed. So p divides y, some prime number p. But then that means p divides x and p divides y. But that doesn't work. So therefore, no number, no prime number divides x. So that means x is equal to 1 or negative 1. Because any number bigger than 1 or negative 1 or less than negative 1 has prime factors. And that also means x squared is equal to 1. So let's put that into this. Oh, then we know p plus 2y plus y cubed is equal to 0, which means d is equal to negative y times y squared minus 2. And so that means we can now substitute back into these two equations. X is equal to xd, which is equal to, um, remember x is 1 or negative 1, which is equal to negative y times y squared minus 2, or y times y squared minus 2. And y is equal to yd, which is equal to negative y squared times y squared minus 2. Um, let's substitute this back into the original equation. Noting that x squared is always y squared times y squared minus 2 squared. So now, if we substitute it back, we don't need to consider the negative or positive case. X to the 4 plus 2x squared, this is the original problem. That becomes y to the 4 times y squared minus 2 to the 4 plus minus 2y to the 4 times y squared minus 2 cubed minus y to the 6 times y squared minus 2 cubed, which is equal to 0. And we can cancel out the y to the 4, making it into y y squared minus 2 to the 4 minus 2 y squared minus 2 cubed minus y squared minus 2 cubed. And we can also cancel out the y squared minus 2 cubed to make it into y squared minus 2 minus 2 minus y squared. That's quite problematic. What happened? That's equal to negative 4, which is not 0. Okay, let's check our steps. Oh, the error appeared quite instantly. These were all meant to be plus. 0. And we're done. So xy is equal to y plus or minus y times y squared plus 2. And y is equal to negative y squared plus 2. For any y, big Y. And now we're finished a bit early, so I have some spare problems that you can watch me do. Maybe it's helpful. Okay, so I'll get out a problem. Um, hmm, okay. Um, is a big list of problems that I found. Problem one, show that for every, and we probably won't, I won't go through all of them by the way. Show that for every integer n bigger than 1, it is possible to write 1 over n as the sum of two reciprocals of distinct positive integers. So how would I approach this? Let's say n is equal to 2. then 1 over 2 is equal to the sum of two distinct integers, a and b are distinct. Now, remember that problem? How to write 1 as the sum of three distinct reciprocals? This looks quite similar. So we already realize we can bound it, right? In general, 1 over n equals 1 over a plus 1 over b, where a and b are distinct positive integers. And a is like still equal to b. So let's try that. If we go back to count, then let's say a is equal to 3, then that means b is equal to 6. Let's say a is equal to 4, b is equal to 4. If a is bigger than or equal to 5, then too tiny. Sign is too tiny to become a half. And this doesn't work because they have to be distinct. So we got this solution. By the way, if a distinct condition doesn't exist, you can just always do this. Right? These are indeed two reciprocals, and they sum to 1 over n. That's why it's quite important for them to be distinct. Let's try n equals to 3. If a is equal to 4, b is equal to 1 over 12. A is equal to 5. B is 1 over b is equal to 2 over 15. Doesn't work. A is equal to 6. B is equal to 6. Not distinct. Else, too tiny. So we got this solution. If n is equal to 4, then a is equal to 5, and b is equal to 1 over 20. By now, we should realize when a is equal to n plus 1, it always works. And that is actually our only answer for the past two cases. So let's quickly check what happens if a is equal to n plus 1. A is equal to n plus 1. Then 1 over n is equal to 1 over n plus 1 plus 1 over b. Means 1 over b is equal to 1 over n minus 1 over n plus 1, which is equal to 1 over n times 1 over this whole thing. And indeed, we always have a solution. 1 over n is equal to 1 over n plus 1 plus 1 over n times n plus 1. Problem 1, done. Problem 2, instantly. That's Simon Favorite's factoring trick. Alright, move the various variables to the same side. Moving the variables to the same side is always useful, by the way. Obviously for Simon's favorite factoring trick, we need to move them to the same side, but in general, it's always a good idea. Okay, so then let's multiply everything by the first coefficient, which was the general method I explained. And then we get this. So we know it has to be a factor of 12. And note, it can't be 1 because that would mean x is equal to 5 over 2. Can't be 3 because that would mean x is equal to 7 over 2. In general, this can't be an odd number because this is divisible by 2. So we can remove those. And then in the corresponding, no, y. In the corresponding cases, we get 6, 3, 2, 1, -6, -3, -2, -1. Um, okay, so let's go through each of these cases. In this case, we get 3 and okay, another thing we notice, this cannot be equal to 6 because we have an even number minus an odd number, which is always an odd number. So now we lose that case. We also lose this case. We lose this case. And we lose this case. Okay, so now let's look at this case. 4 and 3. We get x is equal to 4, y is equal to 3. Next case, 12 and 1. We get 8 and 2. Next case, -4 and -3. We get 0 and 0. Next case, -12, -1. We get -4 and 1. And that's all of our solutions. Okay. X squared, x minus y squared is equal to x plus y. Oh, this one seems quite a lot harder than the other ones actually, so I don't know how helpful it would be to show you the answer for this one. Hmm. Yeah, let's do problem 4 because I can immediately tell that would be very educational. Find all ordered triples of positive integers such that each of them is a factor of the sum of the other two. A divides B plus C, B divides C plus A, C divides A plus B. What do we notice? We notice these three variables, A, B, C, they are the exact same. They do the exact same thing. So we can do a log A equal to B, next to equal to C. How could we use this? Big numbers don't normally divide small numbers, right? Like immediately you know this does not divide 5. Quite obvious. So let's look at this one. C divides A plus B, which means A plus B should be bigger than or equal to C. But A plus B is less than or equal to 2C. So, oh, actually, no, this isn't important. A plus B is a multiple C. So A plus B is equal to C, 2C, 3C, 4C, and so on. But A plus B is less than or equal to 2C. So therefore, A plus B is equal to C or 2C. If A plus B is equal to 2C, A and B should both be less than or equal to C. So that means A is equal to B and B is equal to C. So we get the answers B, C, C. And obviously, this always works. What if A plus B is equal to C? And then we get um C divides A plus B, which is equal to C. But now let's look at the other conditions. B divides C plus A, which is equal to A plus B plus A. So B divides 2A. And A divides B plus C, which is equal to B plus A plus B. So A divides 2B, right? Because B divides 2A plus B, and B always divides B, so we can just take out the B. That's how we got this and this. But now we got another interesting condition. B should be bigger than or equal to 8, but B divides 2A. Means 2A is equal to B or 2B. If 2A is equal to B, let's say 2B first, and A is equal to B, and C is equal to 2A. So we get the solutions AA 2A, which again also works. Else 2A is equal to B, and C is equal to A plus B, which is equal to A plus 2A, which is equal to 3. So we get the solutions A, 2A, 3. This also always works. You can get this by just sewing it in. So in the end, these are our three solutions. But of course, we have to reorder them. So we got this one, and we also got this one, but this has different reorderings. And we also got this one. Those are all of our answers. Okay, that's it for today's lesson. If anyone has any questions, feel free to ask. Otherwise, goodbye. You're welcome. You're welcome. Thank you. Thank you.